So today I'm making what I'm hoping is going to be a very short video on the Heathkit solid-state VOM model IM-25. I already did a two-part video on this, I think back in 2020, where I talked about the restoration of one of these and the things I did and various aspects to it. I talked about the circuit theory and so on, and as part of that project, I'd actually acquired several of these things on eBay, and ever since I did the first video, I've been slowly working my way through all the other ones with the intention of getting them working and reselling them on eBay. And one after another, I'm encountering pretty much the same kind of things on these, so I thought I would just sort of encapsulate those bits of experience into this video. The first thing is about the probes. Probably the original probes on these are shot or missing if you acquire one, and I tend to buy this probe set here, VTVM IM series for Heathkit, so that's the Heathkit IM series. It covers all those VTVMs, and they've now started listing it as working with the IM-16, which is sort of a stripped down version of this IM-25. And the IM-25 itself, solid-state VTVMs. It's a high-quality product. The price is fairly reasonable, and so right off the bat I'd suggest getting that or doing something similar, but you don't have to buy them. The one thing you do have to do one way or another is when you're measuring DC volts with this, only DC volts, you need to have a dedicated probe to that, which incorporates a 1 megohm resistor right up by the probe tip. So the resistor connects to the probe tip, then there's the resistor, and then the lead coming from the meter goes to the other end of the resistor. You don't want to put the resistor down inside the plug. It needs to go right up near the probe for best results. And then another probe, which is usually labeled for AC volts and ohms, and that's based on the VTVMs, which don't have current function. They can't measure current. Very rarely do they do that. So they can measure ohms and AC and DC volts. And so the probe will be labeled AC/ohms, but in fact, if you do use it with an instrument such as the IM-25, which can measure current, milliamps, this is also the probe to use for that. So for every mode you use this probe, except for, and that's the one without the resistor in it, except for DC volts where you have to have the resistor in it. Now this particular supplier brings all three leads, that's the ground lead and the leads for the black and red, and brings them all into one 1/4 inch tip sleeve, or TS, phone plug. Just like you'd use, actually it'd be almost like a set on a traditional pair of headphones, but telephone switchboards and some older audio equipment use this. They're still very common. So instead of doing something like this, you could make two probe sets, one with a ground lead and the red probe for DC volts, and then another plug with two leads, one with a ground lead and the other for a probe for everything except DC volts. Or you could merge them like this. The way Heathkit did it was they just had the two wires coming out. They actually used a shielded cable with the center of the shield being on the tip and the shield of the cable going to the sleeve here. And then there would be a single probe at the end with a switch built into it, and it always had the 1 meg resistor between the center of the shielded cable and the tip, but if you slid the switch, then it would short out that 1 meg resistor, so it's as if it isn't there. That's another way of doing it, but those probes tend to be bulky and probably more trouble than they're worth. So it won't work correctly if you use the wrong kind of test lead/probe setup. And it certainly won't work correctly if you try to use the probe with the 1 meg resistor in it for anything except DC volts. AC volts goes through a separate circuit, which doesn't want that 1 meg resistor there. Current certainly doesn't, and if you have a resistor of 1 megohms and you're trying to measure resistance, you've automatically added 1 megohm to whatever you're trying to measure, so that's no good. So again, only the DC volts measuring function of these meters needs to have that 1 meg resistor in there. I've rarely found there to be any problem with any of the switches on the front panel. I spray a little deoxit in it, they're good to go. I've never had a problem with them being flaky. This 10-turn potentiometer, which has got a thumb wheel on it, I've never had that be a problem. The meter itself always seems to work just fine. As for the back panel, now this one's been modified by me to have extra wires going between the back panel, so it's easier to pull it further away from the meter for servicing, and actually I put Molex plugs on each of the 2-wire sets so they can actually be unplugged and taken far away when you're trying to troubleshoot this part, change components out. You don't need this big thing flapping in the breeze. The other thing I add is a fuse. I just put a fuse holder right on the back and bring the hot lead over to the fuse, and then from the fuse, then the wire coming up to the circuit board. Heathkit just didn't put fuses on things back in the day. They should have, but they didn't. And I think putting it on this way makes sense rather than trying to bodge it onto the circuit board. And then finally, the IM-25 is notorious. If you got it in its virgin state, the whole back of this panel on the inside is full of battery holders. From this one hole all the way up to there, and actually beyond that, is a great big double wide battery holder that holds C-sized cells, C cells. And I believe it holds 16 of them or something. I forget exactly how many. So there's 12 batteries there, or 12 C cells to get the 18 volts. And then there's, bolted on right here where those 2 holes are, there's a similar holder, but it only holds 2 C cells for a total of 3 volts. And that provides the excitation voltage for the ohm meter circuit. In other words, it provides the current that goes out through the resistor under test. In addition to those batteries, and the main battery provides power for the actual active meter circuit. The front end doesn't use any power except for a tiny amount used by the AC converter that converts AC to DC. On these guys down at the lower right corner, you can see where one has been removed, will be a battery holder, or it just holds a cell, but it's an oddball cell. It looks like a stack of button batteries, and it provides 1.35 volts. It's very precise. It's actually used for calibrating the meter, but that provides a reference voltage. It's not really used in the normal sense of a battery. It's just providing its own reference voltage of 1.35 volts to a transistor circuit that provides a constant current. That's also part of the ohm meter circuit. So you need all 3 batteries, and they're a pain. You can't get these anymore. You can buy an alkaline battery that is essentially a stack of cells, but it adds up to 1.5 volts, which is too much. And if you put that in there, the ohm meter circuit won't work correctly. So I just remove those when I restore these. Nobody wants to cart around that many cells, 14 C cells. And the way the battery holders are set up, you have to remove them from the back panel in order to get them open. So it's really a pain to do them. So I put a battery eliminator in there. It's powered off of AC. I just steal it right off the circuit board, right across the primary of the main power transformer. And then I have 2 simple little LM317 circuits that provide 3 volts and provide 1.35 volts. And those get wired up to the places where the normal batteries go. As for the main battery here, I don't have a battery eliminator for that because there's already one inside the IM-25. It's well, it's comprised of that transformer and this filter capacitor and a couple of diodes that are up there, or just one diode. It's a halfway rectifier. You can see it, kind of a bullet-shaped diode. And then these two Zener diodes here and a couple resistors. Those provide the battery eliminator for the main meter circuit. So that's there already. You just need to provide battery eliminators for 3 volts and 1.35 volts, and then wire them up to where the battery's usually connected to if you'd built it the way the factory did it. I would always recommend doing that. It makes so much more sense. Another thing that tends to go wrong with the IM-25 in particular is that the circuit board quality that Heathkit used at this point in time, especially on this model, is really kind of garbage. I don't know if they experimented with a different process or a different vendor or something. It's a very large phenolic board, so it's not structurally very strong. And the foils, although typically very wide on it, don't seem to adhere to the phenolic substrate very well. And it's very common to see lifted foils. And, you know, if you connect the leads up in a funny way, it's possible to blow foils completely off the board, of course. But I'll see a lot of issues where foils have lifted, especially if a component has ever been removed and resoldered or something. You can see, you know, here's an example of a component that had to be removed at one point. The original pad, where that brown circle is, had just come off. So now it was necessary to scrape the solder mask off of the foil, stick a lead through, bend it over, and solder it directly to the foil rather than the pad. And that type of thing is chronic with this model. One thing I would recommend is when desoldering a component on here, and certainly at least some components are going to have to be removed and replaced to resurrect these, when you use a solder sucker on it to remove the solder, then grab the lead and carefully pull it away to the middle of the hole so it's not bending over at all. Because if you try to just pull it out by brute force, and if it's adhering at all to the foil at any point or the pad, it'll pull that force will just pull it right off. The pad will come off and go through the hole along with the lead. So you want to carefully break the leads free from the pad before you try to pull the component out. So that's another gotcha. And because the leads are so fragile, here's another thing that I've learned. When I resolder the various wires from the battery and the AC, Heathkit had them going in on the foil side, and since the foils are not well adhered to the board, it's very easy to lift them off if the wires get pulled at all. So what I always do is drill a hole nearby, somewhere where there's no component, stick the leads through, and then have them come through from the component side and solder them. And then on the back side, or the component side of the board, I'll put a blob of hot melt glue just to secure the leads. Therefore there can be no stress. You can wiggle the wires around all you want and it's not going to damage the foils. So that's another thing to look out for and to be aware of, a technique that I think is useful. If you do end up using a battery eliminator so that this is no longer a battery powered instrument, there's no need to use these two holes here, which are labeled on the board as battery power supply. That's where the leads from the large battery pack with the dozen C cells in it would get wired up to. But if you're setting it up so you're not going to bother with those cantankerous batteries anymore, then you do not need to land anything to those two holes. But the two nearby holes here and here are the ones for the 3-volt battery that's associated with the ohms function. So I drill a hole right here, bring the leads around and solder them in from the component side. And then similarly here, I bring the wires from the 1.3 volt battery eliminator through a hole over here, bring them around and connect them to these holes here, again from the component side. Now these trim pots for calibration, you can see them in the back there. 1, 2, 3, 4, 5 of them. And those are the same ones that are normally accessible along the top here. AC bias, ohms cal, AC cal, DC cal, and DC bias. Those are going to probably need some sort of lubricant on their elements. And I found particularly, and I don't know why it is, I found that the AC bias pot is, you can see it's a little different here. This one has a raised flange. This one has a slightly different supplier. I think these two come from one company. This is another supplier. And this one are yet a different model or supplier. And I found that the AC bias is usually very problematic. It's really hard to get it so that it's working properly. Even after I squirt some deoxit in there, I find that I have to just cycle it back and forth a whole lot with a screwdriver before it starts to behave at all. And if it isn't, you'll find that the wiper is just lifting and it's not even touching the resistive element at all, and you get an open circuit and then crazy results. Unfortunately, these are not very easy to replace, so I just usually put the deoxit in and exercise the heck out of it, sometimes for up to a minute before it finally starts behaving. So that's something else that if one or more of these things are bad, especially the bias ones, the DC bias or the AC bias, nothing's going to work. So that's a common failure point. Oddly enough, this potentiometer over here, this is the zero potentiometer, which goes to the thumb wheel. I've never had a problem with that. I've never seen any dead spots on it or anything. Maybe because it gets adjusted so much in use. So, components on the circuit board that need to be replaced. Guaranteed you're going to need to replace the electrolytic. There's only one big electrolytic on here, and it's for the power supply. It's 250 microfarads, 50 volts, and I use a Sprague Addendum part. You can kind of make out where it says Sprague Addendum there, and it's TVA 1312-EB. I believe that is the model number. It's the right electrical characteristics, and it's the same size as the original capacitor, so it looks authentic. Obviously you can bodge in some other capacitor if you want to, but that's one that I found that fits and works very well here without being radically different. There are 1, 2, 3, 4, 5, 6, 7, 8 at least bipolar transistors in this area. And on the schematic, those are these three here for the current the current regulator, the current sync regulator for the bridge circuit. All three of those can be not necessarily completely failed, but just so far off of their specifications that it just isn't working and you can't get it calibrated. These are often the culprit. Less often are these two and these two. These are the bridge circuit driver transistors, and all the NPN, all the transistors on here except for one FET are all the same model. They are 2N3393. So at least they're a general purpose part. You can probably replace them with many different things, but I found that I have no problem buying those. I usually buy them from Mauser. Mauser always seems to have them in stock in the same type of physical packaging that the originals had, so they look right and they work right. They're exactly the same part. So at least those are readily available. And I haven't found these to be consistently bad, but I've found them to be off enough that the bridge maybe doesn't balance, or you have to go so far to one side of the zero adjust to get it balanced that it's just not right. So I replace these almost always. And this one here is something that often fails. This is the precision current or constant current sync for the high impedance buffer FET here. This guy, Q12, that I've never found a meter in IM-25 where that transistor is working properly. And of course nothing will work if that isn't working properly, so I guarantee you I replace that every time. The other thing I've always found to be at least partially bad is the single FET on here. Actually, there is another one over here. They're both the same model. Those are 2N4304s. JFET. N-channel JFET, I believe is what it is. And strangely enough, I've never had a problem with this one. I've never had to replace it, and it's a good thing because it's not on the circuit board. It's in some impossible to reach, right there about in the middle of the picture, you can see the shiny silver can. It's behind a rat's nest of wires and switches, and you know, that part was wired in when you build the kit before you even mount the switches on the circuit board. When you just set up all the wiring on each individual switch and then mount them on the chassis and then solder the rear ends to the circuit board, all that was done. Once that's done, you can't really get in there. It'd be just impractical, if not impossible. So I'm glad that that one doesn't seem to suffer. But this one here, I've never found an IM-25 yet that where that FET is working the way it should be. And if I pull it out and test it, it's not meeting its published specifications. Luckily, those are available. It's an obsolete part, but there's a lot of surplus transistor sellers. I've been buying mine from Quest Electronics in California. I've not had any problem getting them, and they're even identical to the one that Heathkit provided. I've seen a number of these where people have already replaced that once with some other type of FET, and while the meter will work, it just seems like it'll be a little off and more difficult to calibrate and so on. I've always found replacing that solves the problem. But it's tricky. It's hard to figure out the pin out, and it's real easy to get it rotated one pin position on the circuit board, just due to the way the circuit board is marked and so on. So you have to be very careful with that. The other one that I found to be bad about half the time is the bipolar transistor that works as the constant current source for testing resistors in the ohms mode. That'll be bad sometimes. And you can tell because if you find that you cannot calibrate the ohms function, that is almost certainly the culprit. Assuming you're working with a meter that has worked at some point in the past, that it has not been assembled incorrectly from the get-go. You know, if you get an old one that has been working and shows signs of being in service, but you can't get the ohms function to work properly, that is probably the culprit. I've never had anything else in that circuit go bad. Heathkit is using the bipolar transistors as diodes in several places. It's using two of them here with the bases cut off, just having them connected collector to emitter and in inverse parallel, and that's acting as a voltage clamp in case the voltage on the gate of the FET gets too high relative to circuit common. Then those will conduct and kind of short it out to protect the FET. And a similar thing happens down here with these two that are going to B- and are protecting this FET. I presume those things are working. I've never replaced them, and the main reason I don't replace them is, once again, they tend to be in inaccessible positions. Although some of them are better than others. Two of them are right here. There's three transistors here. It's the rear two that are sort of facing each other. The other ones are again up in a difficult to reach place right on the switches. So I don't know if those are working or not, but as long as they're not shorted out, it won't affect the meter. But if you don't replace them, you might find that the meter doesn't actually have the overvoltage protection anymore. But I think it's more likely that those are probably okay, at least okay enough that leaving them in there doesn't hurt anything. And then these two guys are connected base to emitter just to get that diode voltage drop, and two of them are used together to form a temperature compensation for the constant current sink for the bridge circuit. I've not suspected those were bad, but I always replace them anyway if I'm replacing this one. This is the actual current sink, and these are forming the voltage reference for the current sink, even though they're all the same kind of transistor. If I replace this one, I replace the other two. It's cheap and easy to do, and they're very accessible on the circuit board, easy to get at. I do always shoot the switch contacts with deoxit. Makes quite a mess in here. It's hard to get the nozzle where you need it to get, and you end up getting deoxit over everything. Another thing when you're doing calibration on these is that there's a lengthy section in the calibration chapter dealing with these two frequency compensation trim capacitors, C2 and C4. I've never messed with these. I either leave them where they are, or if I find that they're set way off to one side, I'll move them to the middle of their rotation, which puts them at the nominal ideal value anyway. And although the Heathkit manual doesn't address it, other documents from Heathkit say, well, if you don't have access to a square wave generator and an oscilloscope, which you would need to adjust these, just set them to the middle of their rotation and you'll be fine. Well, here's a couple more of these transistors here. Those are the other clamping voltage clamp right there. At least they're close to the front. You probably could replace those, but so many other things are going into the same leads, you probably wouldn't be able to desolder. You'd probably just have to clip the leads off right at the transistor and then solder, tack solder the new transistors onto the old leads. Something like that. There are several small electrolytics. There's one right in the middle of the picture, and there's a couple other floating around in here. There's one way down there, kind of in the middle of the picture. There's a couple more right there in the middle of the picture, so there's a few of them, and I think they're all 10 microfarads. They're also very hard to get at, and none of them are ones where the signal goes through them. They're just offering filtering in places where you don't probably even strictly need the filtering. I've never tested them, I've never removed and replaced them, and the meters work fine after I do the rest of my restoration, so I think either those are still functional enough, or if they aren't, they're failing in a way that doesn't really hurt the operation of the meter. The other capacitors on the board are either like bypass to ground capacitors. This one that looks like an MOV, but it's really a capacitor. I just leave those alone. And then there's some mica capacitors, which those don't tend to go bad, so you can leave those alone. Almost all the resistors are either carbon composite types, and the rest are wire wound. There's a whole bunch of ones, all for all the range selections. There's a whole bunch there, and they wrap around and go down there. I've never seen any issue with those. I have found a couple of times where this resistor here will be replaced with a different value or lifted off the board, and another resistor soldered into the hole, and then the two transistors soldered together in series. And what's happening there, I'm almost positive, is this one transistor here, and that's this one in the ohms circuit that I talked about. That one will go bad. It won't completely fail, but its characteristics will shift enough that you cannot calibrate the ohms function. And some previous owner will decide to try and fix it by increasing the value of this resistor, which is in series with this transistor, and that may or may not do the trick, but I always end up, if I see that, I replace it. I replace the transistor, I replace the resistor with the old one if it's still within specifications, or a new one if it is not. Also, these three resistors here, 1, 2, 3. You can see they're metal film resistors, not the carbon composites that are elsewhere. Those are the ones that surround this transistor here. And I have found them where they've drifted enough out of specification that they're skewing the circuit and you cannot calibrate the meter. So those, again, they're very accessible. They're close to the edge of the board. Their common value is easily replaced. If you put in a 5% resistor, that's 5% tolerance, it's more than good enough. So that's another thing. I've never seen these two Zener diodes. These are in the voltage regulator circuit. I've never seen these two have failed. The silicon diode that's down here, that's the half-wave rectifier for the main power supply. I've never had that fail. The only other diodes in here, I think it's easier to see from the other side. There's two here and these two here. These are germanium diodes. Heathkit calls them crystal diodes. They're germaniums. And they have to be germaniums or the meter won't work properly. But I've never seen these fail. But if you do replace them, make sure you replace them with a germanium diode, not a silicon diode. I don't think it'll work properly. This is a little bodge that I put on every one of these that I restore. When you're looking at the back of the circuit board, the area with all the transistors is right here. And this over here is where these terminals are, where the FET are located. These three terminals are where the constant current sink transistor that's associated with the FET, that's where that's located. And then the resistors associated with that transistor are all in this area. And you've got this one foil that curves around like this and comes up here and then goes across to here. I always cut this foil right about at this position, and I solder on a 2-pin header like that, and just put a shunt on it. What this allows you to do is divorce the entire front end, or segregate the entire front end from the balanced bridge circuit that drives the actual meter. It can help you figure out where problems are, because everything up to the gate of this FET here would be considered the front end. It's the majority of the circuitry. And then after this point, you're in the meter bridge circuit. That's the part that actually swings the meter movement left to right. Everything is very low impedance here. Everything is very high impedance on this side. It's sometimes very hard to tell which area you need to address for repairs. And so what I do is I basically cut that connection right here. From all this junk up to the gate here, I cut that, and that is this foil. Then I put that on so I can, for diagnostics, I can remove that shunt, and now the 2 pins that are under the shunt are places where I can hook up test leads, little mini alligator test leads or microclip test leads. In other words, one of these guys. And you can force inject. Well, first off, you can put a meter or a scope or something on this pin and see what the front end circuit is trying to send to the balanced bridge meter circuit, or you can clip on to the right hand pin and force a signal into the high impedance buffer going into the bridge circuit. So you can totally segregate all the front end and just force a signal into it at that point and see if everything downstream, in other words, all of this stuff, is working properly. And if that is, then you know that the problem's got to be on this side. And vice versa, you, like I said, by pulling the shunt off and measuring the voltage on the left side, you can see if all the front end circuit's doing its job, because it should always be, no matter what you're in, for a full scale reading, it needs to have about, I think it's 0.15 volts. on there. And the reason I would say that is that, well, it's probably not 0.15 volts, but it's a pretty small voltage. It's going to be what this circuit over here expects to see to give a full scale reading. It's a pretty small voltage. So you can measure that and do that. But anyway, so one of the things I do, and it doesn't have components on the board to do it, but I just have one of these little things right here. It's a small potentiometer, 2K, but it could be a 5K or something like that. And then the other two resistors here are the same as this little circuit right here, right in the middle. So this circuit here is symmetrical. These two transistors form the left side of the bridge. These two transistors form the right side of the bridge, and they have to be balanced. If both of them are conducting the same amount, then the meter reads 0. If one of them conducts more than the other one, then the meter will read upscale or downscale from 0, which is usually to the right. But it's possible with this meter to define the middle of the meter movement as 0, in which case this circuit can drive the meter movement to the left at that point. But normally it'll be just going from left to right when the bridge is no longer balanced. And on this side, the input to the bridge is a 18K over a 22K connected between B plus and B minus. That's essentially the battery voltage, or the output of the internal battery eliminator. It's 18 volts from there to, I'm sorry, it's 18 volts from the battery. It's 9.1 volts from here to here. So if you consider the circuit common to be your measurement reference point, then this would be 9.1 volts. So this just forms a voltage divider, 18K over 22K, and it should always be at 4.9 volts or something pretty close to it. This particular meter in front of me, it wants to sit at 5.1 volts. And that's fine because you can adjust that out with the adjustments on the meter to make it so it balances at that voltage. But normally for a reading of 0, you want this voltage here to be 4.9 and this voltage here to be 4.9. And when you do that, the meter should read 0. Then if you wiggle this voltage up or down from 4.9, then the meter movement will swing left or right. So a way to test this is measure what the voltage is here, take note of it, 4.9, 5, 5.1, whatever it is, and then arrange to have the same voltage here. And what I usually do is I just connect a little adjustable voltage divider between B plus and B minus, just like it is over here. And that's this here. In this particular instance, this is a rheostat, not a potentiometer. It only has 2 terminals. So I just connect the 2 resistors up to its 2 terminals and then clip on and measure from either this lead or this lead, whichever one I can adjust with the pot or the rheostat to be the same voltage as the other side. Again, 4.9 volts or whatever it is. And adjust this to obtain that voltage. These 2 outer ends of the resistors, where I'm holding it, and this other one over here, just get tacked across the power supply. Right here, this foil along the back of the board is B minus, and this foil up here that makes this left-hand turn is B plus. So I always scrape a little of the solder mask off here, a little bit here, and then I connect that resistor potentiometer combination from here to here, and the middle of it, which is usually again nominally 4.9 volts, gets brought over with a alligator clip or a micro clip test lead to the right hand terminal here. So that's driving directly then into the FET. And by swinging, when I have that, then the meter should be working and giving me an indication of 0. And if it is, then that suggests that the whole balanced bridge meter circuit's working correctly. And then if I tweak that potentiometer here, or the rheostat, up and down, I should be able to move the meter left and right. And if that's working, and if it does balance when it's at 4.9 on both sides of the bridge, then you know that side is working properly, and the culprit is over on the other side of the board, or the left side of the schematic here. And again, if you can't, the first place to look at is that one FET. That is almost always a culprit. That guy right there, which is this one right here. And by the way, here are an example of two of those bipolar transistors with the base is cut off, and they're just functioning as a diode. And so again, that happens several places in this circuit. Either on the circuit board, here's another place, or on the switches in the actual discrete switch wiring. One of the most common problems I've seen with these meters, and actually I think every one I've worked on out of the several I've done, all had the same problem out of the box. As soon as I would receive them from the thrift store or the eBay seller or wherever I'd get them, you'd plug it in, you'd put it in voltage mode, and you'd set it to some value, or some range, and you'd hook the test leads up, make sure it's the right kind of test lead, and turn it on, and the meter goes prang really hard over to the right hand side and just pegs. It's like way over here past the scale. It's and that is caused by either usually by the FET being bad, or by something in the balanced bridge circuit being bad. You cannot adjust it out. If it's pranged over to the right like that, and you follow the Heathkit calibration instructions from the manual, which involves the DC bias potentiometer here and the zero adjust here. If using those things, you cannot get the meter from pranging over to the right. Again, that's the most common failure mode in my experience on these things. It could be caused by several things, as I've already talked about, but you're almost guaranteed to have that happen. The only other thing that I've had trouble with on these, it's been on about half of the meters I've looked at. There's a point in the calibration instructions just before calibrating the AC function. They want the AC bias potentiometer to be adjusted, and you do that by finding this one resistor right there, the one that's right in the middle of the picture, the 47K resistor there, orange violet, yellow violet orange, and it's connected to this point where the white wire is going to it, right in the middle of the picture, and that junction over there that's right in the middle of the picture just to the left of the green wire. You can kind of see the lead from the resistor going to it. You clip onto that with a separate voltmeter. It has to be a high impedance voltmeter, like pretty much everybody has now, a digital multimeter of some sort, and you're supposed to adjust the AC bias control here for exactly 6 volts across that resistor. And that's actually this resistor right in the middle of the picture. And there's the AC bias control there. I've sometimes found where I cannot adjust that to 6 volts. And because it's going to be the fault of that transistor if it doesn't, almost for sure, that FET there, Q1. And that's in such an inaccessible place that if I'm getting that where I cannot adjust it for 6 volts, I adjust it as close as I can using the pot, and then I do some checks to see how accurate the AC metering is. And usually it'll be pretty close, but when I turn around and resell it, I just say, because of the inaccessibility of this one part that has failed or partially failed, the AC voltage function on the meter is no longer meeting its specifications, even though it gets pretty close, and could still be useful if you're just not looking for very high precision in the reading. And so that's something which is not likely to fail, but I have had certainly one fail, the one I restored just before this one had that. Maybe another one too. I lose track. But, so there's that. I don't think there's much else I can think of on here that tends to be the problem. I think I've outlined everything that I've experienced to be problems on here. And hopefully this bit of a ramble is of use to somebody. Oh, a bit of a postscript. Another thing which tends to be bad with these, but not electronically, just physically, is they tend to be very dirty. Every one of these I've received has been clearly in some shop somewhere, not an electronics lab, but somebody's been buying them and it's been sitting on a shop that's got a lot of dirty stuff in it, and, you know, oily fumes, and, you know, people setting their coffee cups on top of the meter and things like that. It'll have all sorts of damage of that sort to the exterior of the meter. And one of the things that I've found that goes bad on there, it's the paint on the top and bottom clamshells. Here's one. So I stripped the paint off of these using, you know, paint remover chemical, and then I shoot them with a primer and then give that a light sanding, and then sometimes I'll use, instead of a primer, I'll use a textured paint, something that gives like a bit of a wrinkle finish or a slightly textured finish, and then I'll paint over it with Rust-Oleum camouflage paint. There's a whole line of Rust-Oleum camouflage paints, and I get the one that's called khaki. That's the color. That's a close match to the original Heathkit color. This particular one here, I did not use the textured primer. I just used the Rust-Oleum camouflage khaki right on the bare metal, and put, I think, about 3 coats of it on here. It's okay, but it doesn't have the right appearance because it's missing the texture that was on it originally from the factory. So not a big deal, but I ran out of that when I was shooting these and just decided to hit them with the final color coat only. And I guess I can tack on another thing about physical characteristics. You tend to find that the original screws on the outside of the case, which usually look sort of like this, Phillips head, all of them are 632. Heathkit loved 632, and unless they absolutely couldn't get around it, every screw on the Heathkit will be a 632. And luckily that's a common size, and I buy these screws here from boltdepot.com. Stainless steel, oxide finish, black oxide finish in a 632 by 1/4. That's again the most common size. And I also buy from the same vendor the same product, but with the normal, just simple stainless, no black oxide finish. I just always buy, you know, a bag of these things and use them until I run out, and then buy more. But almost any Heathkit, if you're doing case work and you want to replace the old rusty screws, those will be the 2 you want to get. They'll work for almost everything. Let's see, I don't think there's anything else. Once in a while you'll find that this neon lamp for the power indicator will have failed. It's not too hard to replace. You have to take this one screw out there to get this terminal, 3-position terminal, loose, and then the neon bulb plugs in to the red holder down there, and it's lead solder onto these tabs. But you can't get at it in the first place if that terminal is in there, so you have to remove the screw, and it's a royal pain in the behind to get the lock washer and the nut back on there, but with a little patience and a lot of cursing you can do it. And I should tell you, this is the kind of bulb you want to buy. It's a well, it's often called a C2A, but I think it's more often called an NE101 or an NE2H. Any of those will work. Neon bulbs, sort of a commodity item. They look like that. So I find enough of those failed where I keep a bag of those around too.